today is a great Chi from Purdue University. So his expertise is on uncertainty quantification, data assimilation, and this is what he's going to talk about today.
Thank you, Lee, and thank you very much for the invitation. It's very nice visiting here, and the weather is beautiful. So today I would like to discuss some strategies, specifically developing reduced order closure models for predicting uncertainty quantification, data assimilation of turbulent systems. So this is a joint work with Jianguo Liu from Duke. And so first, I would like to give you a general overview about the intuition and general picture of the problem. So what I would like to do is considering prediction and quantification of uncertainty in such type of so-called turbulent systems. And generally speaking, the system will involve a high-dimensional multiscale state space, and also these multiscale states are coupled by linear and nonlinear interactions. So it will usually lead to very complicated phenomena. And here I give you two typical examples. And these are all simulated results, but closely related to reality. So on the left, it's a so-called Rayleigh-Bernard connection. So it's a water tank. And if you heat up the bottom and cool down the top, so you can imagine the warm water in the bottom will rise and get cooled down on the top and then goes back. So it induces this large scale convection. But very soon you will observe, I don't know whether it's clear here, there is first a coherent large scale structure developed, but also on top of the large scale structure, there are these vertices of different scales and closely coupled together. So this is a general illustration of the phenomena, but this phenomena is actually quite universal in our nature and also various engineering systems. So give you this, another example on the right. So this is the illustration of the ocean jets. So this is the white strips are the streamlines of the fluid field. And you can observe there is this dominant zonal jet structure. And this structure is actually very impactful for many types of important climate events. Actually, this is the so-called Gulf Stream that brings the warm water to high latitudes like the east coast of North America and all the way to Europe. That's the major reason the temperature, the weather is much more wilder in Northern America and Europe compared with the region of the same latitude in, for example, China, which is usually much colder. So this kind of phenomena is very important and with high impact to human activity. But as you can observe here, even though this is from vastly different physics, but similar structures can be observed. There are vertices generated with different scales, and these different vertices are closely interacting with each other due to the nonlinearity of the system. So as a result, even though in most of situations, what we are interested in is the largest scale structure, like the strength, the amplitude, the orientation of the jets. But in order to get an accurate characterization of the largest scale structure, usually we will have to dive into the smaller and smaller scales to get accurate prediction. So this is an inherent problem for computation methods in resolving such type of turbulent system. That on one hand, we want to get prediction for the large scale structure, but on the other hand, we have to do expensive computation in the very refined scale to get accurate result. So far it's for the deterministic prediction, that is, we have an initial condition, we have the forcing boundary condition setup, and we do the prediction of one trajectory of the solution. But in practice, this is also not enough because the other issue, that is a strong instability in such type of system. Or in other words, if we have a small amount of error in the initial value or in the forcing perturbation in time, this will be amplified greatly in time. So this gives the deterministic prediction very challenging because anyway, we will introduce errors from discretization, from model approximation, and from different other sources. And with a small error, our prediction will be completely unreliable even after few steps of time integration. So that's why in most cases of practical predictions, we would like to introduce a statistical or probabilistic characterization of the state rather than one single trajectory. But in order to do that, we introduce even more challenging problem. That is, we not only need to resolve a single trajectory, but the probabilistic distribution of the state. And furthermore, it goes back to the nonlinearity of the model, it will induce non-Gaussian probability distributions. And that's much more difficult compared with Gaussian statistics, because in Gaussian, you just need to consider two characteristics, that's the mean and the covariance, right? But if it's non-Gaussian, it will be a whole spectrum of characteristics, including all the higher order moments. So that's in this talk, my closure problem. So it's a moment closure and closely related with non-Gaussian statistics as extreme events. So if we want to predict statistics, we need to consider not only the central region of the PDF, say, but also the tail region of it. And in the same fashion, the tail region with low probability may have a strong or important non-negligible feedback to the leading order moments. And on the other hand, the extreme events by themselves are also very impactful events, like the hurricanes, extreme weathers. That's something we would like to predict, but they are not as frequent as the major domain of the event. So if we use a sampling or strategy to do that, it's also a challenging task. Yeah, so this is a general overview, and correspondingly, we can ask all these type of questions related to the modeling and mathematical part of this problem. So first of all, how can we quantify the uncertainty in such a system and characterize the model errors? And more importantly, how can we propose some accurate and efficient computational methods to do the both deterministic and statistical forecast? And also, we need to consider the system's sensitivity and the robustness to perturbations. And finally, the data will enter the picture, use data to help us improve our prediction, considering different type of quantities we are interested. So these are, generally speaking, the type of questions we want to address. But of course, these all very challenging and difficult problems. And I'm not that ambitious to address them all. But what I would like to do in this talk is to give you a simplified mathematical formulation that can characterize some of the key phenomena we are interested, included in that more general universal examples, and propose one efficient closure method to capture part of these features, and finally to introduce some data-based method that is to combine data to help us improve the prediction, but also use the model to guide our prediction, not just use the data for empirical forecast. So we can first do the general setup of the problem, and this is a formulation I would like to start with. So this is given by a finite dimensional PDE or SDE actually, but in fact, this is derived from PDE such as Navier-Stokes equation or the flow equations from geophysical or plasma fluids. The idea is the first step we will always need to introduce some discretization or finite spectral truncation of the continuous system and project it into each, like the Galerkin or Fourier modes of finite element grid points values, and it will always end up with a finite dimensional vector field, but the dimension of system will usually be very high, right? So that's the key. The dimension is a very large number. And to summarize it in a abstract way, there is a linear effect. And here I'm using examples from geophysical flows, but in fact, it can include many other type of system. So stick to this example, the rotation dissipation effects can be characterized as a linear part, and usually the energy conserving part is a skew symmetric matrix or operator, and the dissipation is a negative definite part. And also there are different type of forcing terms. So this is also in convention, we decompose this into a deterministic part, and all the unresolved effect is a white noise. But the white noise is not essential, but the most important factor is actually from the nonlinear term. And here also we give some simplification. We assume the nonlinearity is this quadratic bilinear term. And this is actually reasonable because if you think about the Navier-Stokes equation, the nonlinearity is from the advection term, the u dot greater than u, right? And that's exactly the quadratic bilinear coupling. And it's the same under the finite dimensional discretization. And furthermore, this truncation conserves the energy. And so here is putting it in a general way, the inner product defined by the energy with the quadratic term and the state is zero, inferring the conservation of energy. So this is another property we will exploit in constructing the methods. So the difficulty of the problem is, so there are randomness. So either from the forcing or even for a deterministic system, there could be randomness in the initial condition. And this initial condition will be combined with this quadratic nonlinear term. So this quadratic nonlinear term will induce instability to the system, so that even though we start with a Gaussian or synchronized Gaussian distribution like a delta function, the uncertainty will be amplified in time, so that it will lead to a lot of complicated phenomena and non-Gaussian distributions. And the question we want to ask is, first, how can we characterize such type of uncertainty in the system? And most importantly, how can we predict the statistical distribution of the state U following the SDE or ODE like this? Okay.
So is there any spatial variable considered in the system?
Variable?
Spatial location.
Yeah, so there originally should be a spatial variable x. U is a continuous field about x, and then we do the discretization of x. So it's ux1 to xn with the number of grid points, and we put that in a vector that is my u here. Yes, thanks, and let me know if you have any questions. So this is the most straightforward approach to find the PDF of U. That's to write down the Fokker-Planck equation. So it's in the form like this, right? But it's to rewrite a high-dimensional ODE to a high-dimensional PDE, right? To make this problem even more difficult to solve. But still, there are some ideas we could use to address this, to directly solve this Fokker-Planck equation. So first, the standard way of the most straightforward idea is we assume the PDF to be Gaussian, or at least near Gaussian, so that we just need to compute the mean and covariance. So this PDE can be further reduced to a coupled system of ODEs, but still, so it's still a high-dimensional coupled system, which is not easy to compute directly, still, even for Gaussian, and for most of cases, as I will show you, the non-Gaussianity will be playing a central role. So the Gaussian approximation is not usually very desirable. And another approach is to consider each level of marginal distributions. So we can first have the first level marginal distribution, and it will be coupled with a second marginal distribution, and it can be coupled in the way due to the nonlinear coupling term, right? So it will end to a hierarchical type of equations to solve it together. So that's another way to solve that, and it can deal with non-Gaussian statistics, but the computational cost is still there, right? And the common idea or most direct idea to deal with the problem of high dimensionality is using ensembles or Monte Carlo type of approach, right? So if we, instead of running the PDE here, we just run an ensemble simulation of the original system and do the empirical average of the state. But the ensemble size, when the dimension of the system grows, the ensemble size will also grow exponentially actually with it. So in general, there is also a very challenging problem. And what I want to do here is actually combine this type of different ideas. So both keep the lower order, so the mean and covariance, the Gaussian part of the information, but without neglecting all the higher order moments to achieve a closure model, but still hopefully to maintain the computational cost in a affordable level. So that's the ideal or the ultimate goal, but I won't claim I totally address this, but some approaches to get more understanding and ideas about that. So here is a further illustration of the ensemble approach. So what we did is we start with an initial distribution. So it could be even Gaussian, and sample this Gaussian distribution, and then run each sample according to the SDE. And because of the nonlinearity of the system, usually, always as always, this Gaussian distribution will develop non-Gaussian features. And if we use ensemble method to do this type of prediction, what often happens is the particles will clustered into groups, focusing on the part with high probability. And the region with low probability will usually have very few samples or even no samples. And this actually, I will argue, lead to some disastrous result, because this region with low probability first represents extreme events. That's something sometimes we want to predict, right? But the sample is insufficient. And furthermore, even though we are most interested in the leading order moments, but an insufficient characterization of these low probability regions will also lead to large errors in the probability prediction of leading moments because of the nonlinear term. So that's some inherent problem I want to show you or convince you from this type of problems. And here is just to give you a practical illustration for this kind of method. That's to tracking a hurricane. The hurricane actually, it's the realistic trajectory of hurricane is just one deterministic result, right? But what we usually do to predict it is instead we run an ensemble simulation, and the ensemble mean will track the mean trajectory of the hurricane, and the spread or the variance of the ensemble will give us some characterization of the uncertainty in our prediction results. So that's a common way to do that. And as you can see, there will be these outliers happening, and how to characterize the probability of these outliers, and how to characterize how reliable our ensemble average prediction is always a central issue, and it's still largely an unsolved problem. So So this is so there are different ways to solve this, and what we propose here is to introduce decomposition of the state. So U is original stochastic precise, and what we do here is we decompose U into a mean, statistical mean. That is the pointed bracket is expectation about the probability distribution P, and we summarize all the rest part as fluctuation mean zero stochastic process. And furthermore, we can introduce a set of bases VI. You can use them as a Fourier basis or any Galerkin basis. And the ZI is stochastic coefficients characterizing the randomness along each eigendirections. So the second order moments will be summarized as a variance Rij here. And then you just put this back into the original system, and it's a simple application of the Ito's formula. You can derive the equation for the mean like this, and the equation for the variance as a second line. And so you don't need to remember the details of these formulas, but what I want to show you is the central role of the nonlinear term. So in the mean equation, there is a quadratic coupling that leads to the second order moments. And if you write down the equation for the second order moments, there will be this nonlinear term, and the explicit expression is written down here. So you don't need to remember the explicit formula, but what I want to show you is this term will include all the third order moments. And this third order moments, if we want to use this type of closure model of this moment model, this term is very important, and you can observe it from this equation. So the first part, the linear or the quasi-linear part, is written in this way. So it includes a mean and the interaction with the modes. And this operator usually contains instability, meaning that the eigenvalue of this operator could contain many positive values. And then it will amplify the variance, that is, amplify the uncertainty of the system. And if this term is zero, it will just be exponential growth, and the system will finally blow up. And then the third moment is actually a stabilizing effect of the system, so that the final equilibrium distribution can be reached. So this is actually a central term that we should not ignore, but at the same time, to get an accurate approximation of computing this term will include all the third moments that is in general very expensive or difficult to approximate. So this now the central issue is how to approximate this nonlinear coupling term in this system. And oh yeah, so here I just want to give you one example. So this is a so-called two-layer quasi-geostrophic model, but it's just derived from the two-layer shallow water equation, and it's from very similar mechanics. And the two Qs are you can view that at the vorticity in the upper and the lower layer of the shallow water, and this linear effect beta is the rotation of the Earth. Capital U is the mean flow, and the right-hand side are the dissipations, the damping frictions of the boundary condition. And the nonlinearity is from these Jacobian terms. So that's the Vection term from the shallow water equation. These are exactly the same. And what I want to show you is this typical snapshots of the fluid field. So if you run the simulation and get the 2D plot of the vorticity field, you can see the picture like this. So even though this is a deterministic system, you see the solution looks like a random field, right? So that's some intuition why we want to write it in a stochastic process. And also we can use this to illustrate this energy coupling mechanism. So first I compute the eigenvalues of this linearized operator, which is in this picture. So these yellow values are positive, and it means there are strong instability. So this is projected in the Fourier modes. So I assume double periodic boundary condition, just for simplicity. this is the wave numbers in X and Y. The instability is induced in the kx direction. So the energy in this mode will grow exponentially in time. And also I plot the third moment's feedback, and you see along the directions with the strongest linear instability, the third moment gives the negative values. That is a stabilizing effect. Right? And in the orthogonal direction, when the linear factor is stable, the third moment is in positive values, so that it is acting like a energy source term to inject energy into the system, so that all the scales of the system is connected in this way. So first, there is a linear growth of the energy in the linearly unstable states, and then the third moment moves the additional energy in this linearly unstable mode, and inject or transfer the energy to the linearly stable parts, so that there is this turbulent structure generated in the field. And the question is, how can we propose or construct efficient models to compute or capture these kind of features, at least in the largest scales, but without too much computational cost. So far, so good. And there are many related works, so I think I will skip. And so here, to summarize the difficulties, we would like to propose an ensemble-based approach. So first, it's adaptable to different methods, and also it is easy to implement. But the problem is it's also very expensive to run a large number of ensemble. So we would like to reduce control the ensemble size in a small amount, but the curse of dimensionality tells us if we use an insufficient number of samples to approximate the full state, usually the samples will collapse or clustered in some region, so that the prediction will be a failure. So that's the inherent problem we want to deal with here. And here, our strategy is essentially follow the two steps in data assimilation. It's vaguely speaking, we first do a forecast step, so to move the model in one time step to get the forecast state or the prior state of the distribution. And second, we do the analysis step, that is to use data to correct our prediction, so that we can have some kind of optimal approximation estimation conditional on the partial observation data, and then repeat this procedure. So next, I would like to first discuss the forecast model. That is, how can we get the prior distribution using ensemble method to capture the essential features we want. And the second, how can we include observation data into the general framework and do a refined forecast. So let's do it one by one. And the first step is to develop the forecast model of its moment closure method for the system. So we return to the original equation, and we do the same thing. We do the decomposition of state into the mean and the fluctuation. And then, so previously I didn't show you the SDE for the coefficients, and here I write down this explicitly. And the difficulty is still here. It's this nonlinear coupling term, and Z is a high dimensional vector, and here we want to use the ensemble to approximate it, so we run. We need a large number of n to compute this, and for each, this will include the summation of all the modes. So for each sample, it's some computational cost, and then we need time n with the cost even larger. And then the mean and the variance equation. So first, it can be written in this way with respect to the empirical average of the stochastic samples in the second moment and in the third moment. And here, this is just for numerical issue. We want this covariance and the sample estimation to be consistent. So we add this relaxation term. So I won't talk too much about this, but numerically, this shows very important to given convergent result because of the instability of the system. So this is essentially nothing but rewrite the original system in a new way, right? But so first we can have the consistency result. That is when n goes to infinity, this kind of coupled stochastic and statistical system will give the same probabilistic solution as the original system. So this part is we can check in the first place. That is, we can write the Fokker-Planck for the stochastic coefficients. So it's a new measure rho, and we can show the previous system, the U bar and R, the mean and variance computed in this system is consistent with the original statistics with P is the measure, the probability distribution of the original system, and also the higher moments are also consistent with P, the original probability distribution, and rho is the measure for the stochastic coefficients. So this is a consistency, which means we can use this system to extract the K statistics. And this is given n is a very large number. Right? And now our question is whether we could use a moderate or small size n so that we can still capture the U bar and R in some kind of accurate prediction so that we don't need to run this very expensive ensemble simulation with a very large sample size. Right? So to do that, we seek help. Sure.
Where this relaxation
Yeah. This is adding artificially for the numerical stability. So there is a consistency. By definition, the second moments of Z should be equal to R, right? But here we just write them separately, and this is just marginally stable because this part balances this part. And without adding this term, it's okay, but numerically, it might have some unstable issues. So that's what we find when we writing the code. So we realize, so this epsilon inverse needs just to be a very small number so that it can stabilize the system. And without this, and if the eigenvalue, the largest eigenvalue of this linear operator is large, you are easy to get divergence of the result because of the finite estimate of this term. Yeah. Yeah. So next, we just want to propose an efficient algorithm for solving the previous system, and here is a little detour. This is the numerical method we found originally proposed by Shijin, Jianguo Liu, and collaborators for solving kinetic interacting particle systems. So I just gave you a very quick high-level introduction of the idea, and what they want to solve is this interacting particle system. So Xi is the particles, and they are interacting with this kernel interaction and the white noise. And the n is again a large number, so it's very expensive to compute directly. But what the idea in their method is instead of computing this summation of the large number, they usually the Xi for each sample, it could be some fast mixing or have a rapid autocorrelation time. Then we could decompose the samples into small groups or small batches. So this is a similar idea as stochastic gradient descent in neural networks, right? So instead of computing the summation of all the samples, we just pick a very small portion of all the samples like P to update each sample I. Of course, this contains much larger error than this true result, right? But the next step is we do the resampling after each step of time updating. So when we update each sample using a small sample average, we regroup these batches by randomly joining the batches in another way and then repeat this procedure. So that the idea is we don't want to predict each individual trajectory, but the statistics of the ensemble, right? So that each individual realization is not important, but as long as it keeps accurate in the statistical way, so that we can just compute the samples in one single step and do the resampling. So the time averaging will be equivalent to the spatial average, so that it will give the same statistical forecast. And also it reduces the computational cost because there are n samples and the summation of n. So it's a n square computational cost. And now we just have p batch members in each particle update. So this p is in the order of 10 or below 10, and n is 10 to the 4th fifths. So this is a huge reduction in the model. Right? So this is the original idea, but let's come back to our system. So like this, it's from completely different background, but you observe some similarity here, right? We have this summation of all the modes, and also so here buried in this term, there's also a summation of each modes. And for each spectral modes, and yeah, I forgot to mention a typical feature of the turbulent system is it usually contains a very wide spectrum of modes of a slow decaying rate. That is, it contains the multiscale modes, and each mode may contain a rather large amount of energy. But diving from large to smaller scales, the smaller scale modes usually have a faster mixing rate, meaning they are decoyed in a faster time. And usually we could give the a Gaudicity assumption, meaning that the time average of the mode could be equivalent to the statistical expectation. So that for each wave number, the k here, we could view it as a particle in this case, and then do the same trick, right? So this is the summary of this idea. So previously, we have the in the variance equation, the R had dimension k square, and for each update, there's k square operations, right? So that's the k to the 4th computation, and the ensemble simulation requires n times all these operations. So this is usually a huge number of operations, but in the same idea, we could regroup the wide spectrum into small batches, and in each time updating step, we just run a small portion of it. So it's under the same spirit, we decompose a large number of interaction modes into small batches, and in each step, we just updating each batch, and then for each time step updating, we do all the batch members in a random way, so that statistically it gives a consistency result. So this is a general idea, and what we can do is to write a system like this. So previously, for each stochastic coefficients, we need to do the summation of all the wave numbers from 1 to k squared. Right? But now we just pick a small portion of modes in this summation, both for the stochastic equation and the statistical equation. So, and this is the decomposition of all the wave numbers of the modes. And then for each time, after each time step, we resample the modes. That's the number, we take the summation here. So for each time updating step, we do the resample, and with the time integration, it's like to do a time average of all the samples, so that they give the same statistical moments. And the first of all, the computational reduction will be huge, because previously it's k to the 4th, and now we just need to add an order of 10 member of the samples. So this is a huge reduction. And most importantly, for the ensemble update, previously we used this sample M to sample D or K dimensional space. Right? Now we just need to use that to sample a P dimensional space, which is in a much lower dimension. So that first, this is just a P squared to the K, and then this M is also much smaller than the full model case. And here is just a comment for consistent statistics. We need to compute the coefficients with a scaling factor. That's technical details. And so this is a repeat of the algorithm as I described just now. We start with the initial value and the sample, and then we do the sample update in groups, and then resample it in each time step. And then we can show this this random batch method is indeed convergent to the true statistics in the averaging way, right? So here is the assumption of the model. We assume the instability is not too large and the coupling is uniformly bounded. So that's pretty common for all the system. And this is the energy conservation property we will need for each mode. That is energy transfer from mode K to L should be the same to the L to the K. That's a symmetry we have so that the energy can be derived. And we can show that, so Z is the original stochastic state. So the expectation of the original state is equal to the empirical average of the prediction using the RBM approach. And the error is bounded by the time step, which is also consistent with our intuition, right? If we use a smaller time step, it means we resample the particles in a more frequent way, so it's more accurate. And also because we are using a first order Euler-Maruyama scheme to integrate this, so it is a first order result. And yeah, so I will skip these technical details for the convergence and directly show you one example. So we take this prototype model for our first test. This is a so-called Lorentz 96 system. So it also have a background from climate, but it illustrates a general type of multiscale coupling. So there are two levels of grids. In the inner level, there are large-scale modes, and for each large-scale mode is connected to a couple of small-scale processes, and they are coupled in this explicit way. And this is one realization of the solution. So this is a large-scale U, and this is a small-scale V, and clearly you can see this. So again, this is a deterministic system, which demonstrates quite random phenomena, and you can see the similarity and multi-scale structure of the process. And what we want to predict is to extract at least the mean and the variance of both the large and the small scale states. But as you can observe, the nonlinear term is dominant in this system, so that if you directly do the brutal force closure, the error will be, it is actually an unstable scheme. So, and this is a test result. So we do the random batch decomposition in the larger and smaller scales. So originally, sorry. So the original dimension is 8 dimension in the larger scale, and the smaller scale 258. And in the reduce order model, we choose a batch size 4. That is, we just need to take four modes in the large scale and 16, 8, or 4 in the smaller scale, and do the random batch prediction. So the first row is energy spectral. That is variance of each mode in large and smaller scales, and they have consistency recovery of the spectrum. And you see here this bump is the internal instability for the system here. And furthermore, this is the PDF and other scatter plots for the samples from an extensive Monte Carlo simulation. And you see this model demonstrate highly non-Gaussian distributions. And this is usually extremely difficult to capture if we use a small sample size. And here to get the truth, I take 5 to the 10 to the 4 samples to get this structure. But if you you need some smoothing to get this result. But in the random batch approach, we just take 100 samples, and the PDF structure is also captured in this case. So this is still just a preliminary test, but we think it's promising. So it could serve as a first forecast step for the statistical forecast. So that's the first step. And yeah, so this is a more detailed error estimate, and I will also skip. But so I will quickly say in the second part is what we want to do is to introduce observation data into this general framework. That is, now we have a forecast model which can get the leading moments, the mean and the variance. But the question is whether we can, in addition, introduce some additional data to improve our forecast to help this framework computationally and also to improve the accuracy. So here is a very quick overview for the idea in filtering, and all. In my understanding, filtering is exactly the same as data assimilation, but there are some tiny difference. But the idea is, so we have this coupled process. U is so we first have the truth we want to approximate. So you can view this as a realization of the weather event or any state you want to predict, and the model is this SDE to approximate that. So we start with a distribution and run this model. It gives us another distribution from this forecast model. Of course, there's randomness and instability in the model, so the uncertainty will grow when we integrate the system in time, right? And the idea in filtering is if we have another process Y, which is observation, and it's dependent on the signal process U. So if we can have a data here, but of course the data is first not perfect. That involves different type of noises, and also the data is partial. That is, Y cannot, given Y, U is an undetermined problem to solve. So it is still also given by a probability distribution. And then we do the Bayesian inference for these two distributions, and it can give you a posterior estimate, which can reduce both the forecast error and the observation error. So this is a one-step forecast. And in the filtering or in the dynamical system, we want to do it online in time. So we want to repeatedly doing this procedure in time so that for each step, it need to be efficient. So that's again, the same computational challenging to run filtering model for this. And in the linear system like this, so the dynamics is linear and the observation is subject to a linear operator, there is a formidable result for that. That is a so-called Kalman filter. We can write a closed equation in the form like this. So if you just ignore this blue part, this is exactly the forecast model of the linear system, right? It's a forecast of the mean, and this is a forecast of the variance. And what the Kalman filter formula tells us is posterior distribution is given by these additional terms. So Y is observation, and this is a comparison of the observation of the model forecast. And here is a covariance that is related with the second moment of system. So all the statistics is coupled here, and also in the variance equation is coupled with also the observation operator and the covariance matrix. And it can be shown in the linear setup, this U hat is optimal estimate in the sense it belongs to the G is the observation set. So it's a G measurable, square integrable process. And for all this process, U hat is a minimizer of it. So in this sense, it's the optimal unbiased estimation. And the covariance just gives the error between the optimal estimation and the truth. So it's a quantification of the uncertainty of the system. But so this is very nice, and everything is rigorous. But the problem is there's nonlinearity in our system, right? So so here is a one step to make this a bit more complex. Let's say is to add observation dependent to the system. So this is nonlinear, but it's just in the minimum amount, given that if I give you the observation y, then you given y is still Gaussian and linear process. So it's called conditional Gaussian, and we can write the Kalman filter updating formula in exact same way, and the result can be derived under the same fashion. So this is the equation, and what we want to do is still combine this to our system, right? So here we write it in this way. So Z is a stochastic process that includes all the higher order moments of non-Gaussian distribution. Yeah, I will wrap up with these slides. And the states statistical following this. And this fit very well into the filtering framework. That is, if we can get some access to the observation, that is U bar and R, whether we can use the low order moments observation to recover the stochastic process. So that's exactly fit into the filtering framework. And I will neglect the details, but just give you the idea. That is, we write down again the Fokker-Planck equation of the distribution given the observation. And this, in this level of distribution, it's a linear system, or at least a conditional linear system, and fit into the Kalman filter framework in the functional space. And then we can apply this and write down the equation. So it's a complicated formula, but it's a closed set of equation. And the part I will neglect is technical details to solve this equation, but I can just show you in this result that we can use the observation to first stabilize the system, and using this to use a finite sample to capture the structure of both these near Gaussian and the Gaussian distributions using just a small sample size. So sorry, I very quickly here, and just to summarize. So there are two steps. First, we use high order moment closure for the forecast model, and the second, we can incorporate it with a data assimilation framework that is using the lower moments observation data to get higher moments of non-Gaussian PDF prediction. So, but most of these results are still preliminary, so there are many unanswered questions. So many things are still imprecise. So that's all. Thank you.
Do you mind going back to the moon system, page 13?
13, 1-3.
Okay, there it is. So first of all, I want to make sure that the choice of the basis VK is just the Fourier mode, or is any other more convenient choice?
In our numerical tests, we always take Fourier modes because we can use FFT. So it's just for simplicity of the first test, and and we assume periodic boundary condition. But essentially, you can pick any basis. And actually, what we are considering is we can also even use some basis extracted from data, some neural network basis to do this.
Is there any like the basis will make your moon system even more sparse if you select them?
Yeah, that's a very good idea, which we haven't explored. That is, here we put the complexity in the, we just pick a simple basis. We can have the easiest basis, and just so the difficulty is how to compute these stochastic coefficients. And another approach, and I think is also very promising, is if we can choose well-informed basis, then the process for coefficients can be much so that we can compute the SD and the PD with fewer number of these coupling terms. So that's yeah, I agree. This could be another very promising direction, and I'm actually trying some ideas to train this basis rather than randomly pick that, and yeah, haven't done much about it.
The second one, I have a very naive idea. I do not think this makes sense. Yeah, because in the last equation, basically try to do is the enclose the system, because the third order moment system depends on the covariance, right? So do you think you can replace the third order moments by some neural network, which is trained from the lower order moments? So
yeah.
you don't have to do that the random batch every, the time step. You can basically use the neural network to approximate the time step.
Yeah, exactly. That's something we indeed did. So this related to some of my PhD works actually with Andy Maeda. So that we propose some parameterized. So that is, as you said, we use some parameters of parameterized lower moments to approximate these third order moments, and we can have some theoretical framework first how to construct the. And the second, to what degree we can approximate that using FDT, fluctuation dissipation theorem, and stuff. But the problem is that's kind of, in my opinion, a bit ad hoc, meaning that we need to tune. So first we do an exhaustive searching of the parameters, which is affordable but difficult to generalize to a really high dimensional system like the QG equation. And the second, we need to tune the parameter according to the equilibrium distribution. That is giving you a distribution that is the equilibrium measure of system. We need to tune that, and the prediction is good just around the equilibrium distribution. And if you perturb the system to a large amount, so it will not be that good. So that's the first parameterized model. And the second thing we have tried is, as you said, use a neural network, but also based on the coupling mechanism, because there's instability issues we need to deal with. That's some work I did with John Harlem from Penn State and some others, and that also works in some sense. But I think the problem is also typical as in general in neural networks. It's extrapolation problem. You can train that within the data set and it performs generally well. But I don't know, in my experience, for this kind of test, it's difficult to go beyond the training set. So that's similar to the first case. If you perturb the system to a very large amount, the prediction will not be very good. So that's why we changed to this kind of approach. And I like this approach because it's more adaptable. It's more adaptive to the data assimilation filtering framework in the data and all the particle method tricks we can use. So, but the original parameterized or machine learning models is less adaptive, in my opinion.
Thanks.
Any other questions? Thank the speaker again.
Thank you.